Imagine this. You're riding home after a long day, the streetlights are dim, the road ahead looks smooth, and suddenly your bike jerks violently, a pothole you never saw. You lose balance, your heart skips a bit, traffic rushes past you. For a moment, everything feels out of control. Now imagine something even more unsettling. That pothole wasn't new. It had been there for weeks, maybe months, unreported, unnoticed, unrepaired. And you aren't the first one to hit it. Every day we travel the same roads, the roads that take us to college, to work, to interviews, to dreams. But somewhere along that journey, we slow down near that one pothole. We swear to avoid that long crack. We pray our suspension survives that broken patch. And then we move on. Because we think it's normal, it's India, it's never going to change. But what if I told you those small cracks you ignore today become tomorrow's accidents? Those potholes you dodge have already caused thousands of injuries. And the scariest part, most road defects are never reported, never tracked, never fixed on time. Not because authorities don't care, but because they simply don't see them soon enough. Manual inspection take months, surveys cost lakhs, and by the time repairs begin, the damage is already worse. So I asked myself one question. What if roads could report their own damage? What if a camera, a simple phone, or a vehicle dashcam could automatically detect road defects in real time? What if technology could become the voice of our roads? And that question led to this project. Introducing Marg Rakshak, an AI-powered road damage detection system built using machine learning and computer vision. This project can detect longitudinal cracks, transverse cracks, alligator cracks, potholes, and other road corruption from images, videos, and even live webcam feed. No manual inspection, no paperwork delays, just instant AI analysis. Upload a road video, and within minutes, you will get annotated visuals, damage counts, and actionable insights. But this project isn't just about detection, it's about prevention. Because every crack detected early is an accident prevented. Every pothole mapped is a life protected, and every automated report generated is a step towards smarter infrastructure. In a country where millions travel daily, even one safer road matters. This project combines YOLO object detection, deep learning training, real time video processing, and web app deployment to create an end-to-end intelligence system, from dataset collection to model training to a fully functional detection dashboard. And in this video, I'll walk you through everything, step by step. You will learn how the dataset was prepared, how the model was trained, how accuracy was improved, how video detection works, and how the entire web app was built. So whether you are a student, a developer, or someone passionate about AI for social good, this project will show you how machine learning can solve real world problems. Because technology isn't about automation, it's about impact. And if AI can help fix our roads, it can help save lives too. So let's begin this journey of building smarter roads with smarter intelligence. Because it's not just a time to detect the damage, it's time to fix the roads. Before we jump into the coding part, quick heads up. What you are watching right now is Marg Rakshak version 1.0, and honestly, this is just the foundation because version 2 is already in works and is going to be a serious upgrade. We are not just tweaking the model, we are evolving the entire system. Basically, we are taking this from a simple damage detection project to something that feels like a real world smart city AI system. Now, I won't lie because building version 2 means more data collection, model tuning, testing, retraining, optimization, and the whole pipeline. So, before we start coding version 1, if you're excited for version 2, drop a like on this video, subscribe so you don't miss the upgrade, and comment version 2 so I know you want it. If I see enough hype in the comments, I'll prioritize version 2 and bring it faster. Alright, let's open the code and start building. Make sure you maintain the exact same file and folder structure as shown. Do not rename folders, do not move files, do not change directory paths unless you update them everywhere in the code. Even a small structural change like moving the model file or renaming folder can cause the app to break, fail to load images, or throw file path errors. So please ensure your project structure matches exactly as demonstrated. If something isn't working, the first thing to check is your folder structure. To download the dataset, open your browser and search for road defect dataset. Once opened, click on RDD 2022 dataset by Dataset Ninja. As you scroll down, you can see the images of the road defects and the labels of it. As you can see also there are some metrics, and over here there is a download option. This is a around 13 GB file, so we are not going to download this. We'll click on this GitHub file, road damage director, and then we'll scroll down. Instead of downloading the entire dataset, we'll download a part of this dataset. As you can see over here, we have Japan dataset, India dataset, United States, Norway, China. We are going to download the Japan dataset for this project. Once you click on download, it will start download. Once it is downloaded, open the zip folder and extract the files. Open app.py and write the following code. We began by importing all the required libraries that power this entire road damage detection system. First, we import Flask along with render template, request, and JSONify from the Flask framework. Flask is the backbone of our web application. It handles routing, server communication, and connects the front-end UI with our machine learning model. Render template is used to load our HTML pages. Request helps us to receive uploaded files like images and videos, and JSONify allows us to send structured JSON responses back to the front end. Next, we import YOLO from the Ultralytics library. This is the deep learning object detection model that actually detects road defects like cracks and potholes. Then we import CV2. This is OpenCV used for image and video processing, annotation, drawing, and video writing. After that comes OS. This helps us manage file paths and directories. Finally, we import UUID, which generates unique file names so uploads never overwrite each other. App configuration. Initializing the server. We initiate our Flask application using app equals to Flask name. This line creates the web server instance that will handle all the routes and requests. Then we define two folders. Upload folder where raw uploaded media is stored, and the result folder where annotated outputs are saved. Using os.margdirs exit OK equals to true, we ensure these folders are automatically created if they don't already exist. This prevents runtime errors when saving files. Loading the trained YOLO model. Next, we load our custom trained model equals to YOLO best.pt. This file best.pt contains the learned weights from the training. Once loaded, the model is ready to perform inference on images and videos. Helper function, counting detected defects. Now we define a helper function called count detection results. This function's job is to count how many defects of each type are detected. We start by creating a dictionary called counts with all detected categories initialized to 0. D00 indicates to longitudinal cracks, D10 indicates to transverse cracks, D20 to alligator cracks, D40 to potholes, and others indicates to unknown defects. Then we define a class map. This is extremely important. Your YOLO model output class names like longitudinal cracks, potholes, but your dashboard uses coded labels like D00 and D10. So this mapping converts model labels to dashboard labels. We then loop through detection results. For each result, if not bounding box exists, we skip it. Otherwise, we extract class IDs, convert IDs to class names using model.names, map them using class map, increment the corrected counter. If any unknown class appears, it goes into other. Finally, we return the counts dictionary. Route 1 loading the home page. This route handles the home page at the rate app.root/. When users open the website, Flask renders index.html, your web dashboard UI. Image prediction route. Now comes the image detection pipeline. Route predict image post method. This endpoint receives uploaded images from the frontend. Step 1 validate upload. First we check if a file exists in the request. If file name is not empty, if either fails, we return an error JSON. Step 2 save the image. We generate a unique file name using UUID. This prevents overwriting when multiple users upload files. The image is saved inside static upload. Step 3 run detection. We pass the image path into YOLO, results equals to model uploaded path. The model analyzes the image and detects road defects. We then count detection using our helper function. Step 4 generate annotated image. YOLO provides a dot plot function that draws bounding boxes and labels. We save this annotated output inside static results using OpenCV. Step 5 send response. Finally, we return JSON containing annotated image path detection count. The frontend uses this to display results. Video prediction route. This is the most computationally heavy pipeline slash predict video. Step 1. Validate upload. Same validation as images ensures a video file is received. Step 2. Save video. Again we generate a UUID file name and save it in uploads. Step 3. Initialize video reader. Using OpenCV, cap equals to cv2.video capture upload path. This opens the video for frame by frame processing. We extract, width, height, FPS. These are needed to write the output video. Step 4. Set up video writer. We create a video writer object. This writes annotated frames into a new output video file. Then we save it in MP4. Step 5. Initialize counters. Same detected counters dictionary is created for total aggregation across all frames. Frame by frame processing loop. Now the code detection loop begins while cap dot is opened. This runs until the video ends. For each frame, read frame using cap.read. If frame doesn't exist, break loop. Run YOLO detection on the frame. Count detection for that frame, add them to total counts. Draw annotations, write frame into output video. So yes, the model checks every single frame unless you add frame skip logic. Step 6. Release resources. After processing, release video reader, release video writer. This prevents memory leaks and file corruption. Step 7. Returns results. Finally, we send the JSON containing annotated video path, total defect counts. Frontend then loads the processed video. Running the Flask app. At the bottom, if name equals to main, app.run debug equals to true. This starts the Flask development server. Debug equals to true enables. Auto reloads on code changes. Detailed error logs. Perfect for deployment and testing. Next, we need to convert XML to YOLO format because most modern object detection models like YOLO do not understand XML annotation directly. XML files store bounding boxes in a different structure. YOLO, on the other hand, requires annotation in a .txt format with normalized values, class ID, x center, y center, width, height. Without this conversion, the model cannot read the labels during training. So converting XML to YOLO ensures the annotation matches the model expected format, enabling proper training and accurate detection. Importing required libraries. We began by importing the essential libraries needed to convert our dataset into YOLO format. First, we import OS. This library helps us navigate folders, join file paths, and manage directories across different operating systems. Next, we import xml.etree.elementtree as ET. This is crucial because our annotations are in XML format, most likely Pascal VOC style, and this library allows us to read and extract bounding boxes information from those XML files. Then we import image from PIL, which stands for Python Imaging Library. We use this to open images and get their width and height, which is necessary for converting bounding boxes into YOLO format. After that, we import tqdm. This is not required for functionality, but it gives a clean progress bar in the terminal while converting files. It makes the process look professional and helps track progress when dealing with large dataset. Finally, we import subtle, which allows us to copy images from one folder to another. Defining the final class mapping. We now define something extremely important, which is the class map. This dictionary map dataset classes codes to numeric IDs that YOLO requires. For example, D00 to 0 for longitudinal cracks, D10 to 1 for transverse cracks, D20 to 2 for alligator cracks, and D40 which sets to 3 for pothole. Interestingly, D43, D44 and D50 are all mapped in class ID 4. This means we are merging multiple corruption types into a single other category. This helps simplify the model and reduce class imbalance. YOLO does not understand string labels, it only understands integer class IDs. So this mapping is essential. Defining input and output directories. We define data dir equals to data, output dir equals to dataset. The data folder contains the original dataset, probably structured in train and test folders. The dataset folder will contain the final YOLO formatted structure with images train, images test, labels train. This matches the YOLO's expected dataset format. Converting bounding boxes to YOLO format. Now comes the most mathematical part, the convert box function. YOLO does not store bounding boxes as xmin, ymin, xmax, ymax like Pascal VOC does. Instead, YOLO uses x center, y center, width and height. And all of these values must be normalized between 0 and 1. So inside this function, first we calculate dw and dh, which are simply the inverse of image, width and height. This helps us normalize values. Then we extract the xmin, xmax, ymin, ymax from the XML box. Next we compute x center equals to xmin plus ymax divided by 2. Y center equals to ymin plus ymax divided by 2. Width equals to xmax minus xmin and height equals to ymax minus ymin. Finally, we multiply everything by the normalization factors to convert them into YOLO format. This function returns normalized coordinates ready to be written into a .txt level file, converting the training data. Now we move to the convert train function. First, we define paths to training images, training annotations, XML files, output image directory, output level directory. We then create those output folders if they don't exist using os.markdirs. Walking through subfolders. The dataset might contain nested annotation folders, so instead of just listing files in one directory, we use the os.walk to recursively go through all subfolders and collect every XML file. We store all XML paths in a list called XML files. Then we print how many XML files were found just to verify the dataset integrity. processing each XML file. Using TQDM, we loop over every XML file with a progress bar. For each XML file, we phrase it using et.phrase and get the root element. Then we extract the image file name from inside the XML. We construct the full image path and check if it exists. If not, we print a warning and skip it. This prevents crashes due to missing files. Getting image dimensions. We open the image using PIL, extract width and height. This is required because YOLO coordinates must be normalized relative to the image size. Creating the yellow label file. We generate a .txt label file name matching the XML name. Then we open that file for writing. Next we loop through every object inside the XML file. For each object, we extract the class name. If the class name is not in our class map, we print a warning and skip it. If it exists, we retrieve its numeric class ID. Then we extract bounding box values xmin, ymax, ymin, ymax. We pass these into convert box to convert them into normalized YOLO format. Finally, we write a line into the label file class ID x center, y center, width, height. This is exactly the format YOLO expects. Copying the image. After writing the label file, we copy the corresponding image into the output training image folder. So now, every XML annotation we have an image in dataset image train folder and a label in dataset labels train folder. Perfect for YOLO structure. Preparing test images. Next is the convert test function. Test images usually don't have annotation, so we simply define test image directory, create output test directory, copy all test images into dataset, images and test. So label files are created for test data. Main execution block. Finally we have if name equals to main. This ensures that the script runs only when executed directly. First we print a message that training data conversation is starting. Then we call convert train. After that we prepare test images using convert test. And finally we print a success message confirming that dataset conversion is complete. Alright, now open train.py and write the following code. We start by importing the required libraries from Ultralytics import YOLO, import torch. Here we import YOLO from the Ultralytics library, which gives us access to YOLO training pipeline. Then we import PyTorch because YOLO runs on top of PyTorch and we'll use it to check whether CUDA or GPU support is available. Next we define the device. Device equals to CPU. Here we are focusing the training to run on CPU. This is useful if you don't have a GPU or if CUDA is not configured properly. Then we print two things. Print using the device, print torch CUDA available, torch.CUDA is available. The first line confirms which device we are using. The second line checks whether CUDA or GPU acceleration is available. If it prints false, that means training will run on CPU only. Now we load a pre-trained YOLO model equals to YOLO 11.pt. This loads a nano version of YOLO 11. YOLO model comes in different sizes, N for nano, which is the smallest and the fastest, S for small, M for medium, L for large, and X for extra large. We are using nano because it's lightweight and suitable for CPU training. Larger models would be too slow on CPU. Also notice that the file ends with .pt. This means it is pre-trained model on a large dataset like COCO. This helps us use transfer learning instead of training from scratch. Now comes the most important part, training. Model.train. This function starts the training process. Data equals to data.yaml. This points to the dataset configuration file. Inside data.yaml, you define train image path, validation image path, number of classes, class names. Without this file, YOLO doesn't know what data to train on. Epos equals to 100. This means that the model will see the entire dataset 100 times. More epos equals to more learning, but more training time. Image size is 640. This resizes all the images to 640 into 640 before training. 640 is a sweet spot, good accuracy without being too heavy for CPU. Batch equals to 4. Batch size defines how many images are processed at a time. Since we are using CPU, we keep it low 4 to avoid RAM overflow and system freezing. If you increase this too much on CPU, your system may crash. Device equals to device. This ensures that the training runs on CPU. If you had a GPU, you could set it to CUDA. Workers equals to 2. Workers control how many CPU threads load the data. More workers equals to faster data loading. But too many workers on CPU can overload the system, so we keep it low. Cache equals to false. If set to true, the dataset is loaded into RAM for faster training. But since CPU machines usually have limited RAM, we disable caching to stay safe. Pretrain equals to true. This tells YOLO to use the pretrain weights from YOLO11n.pt. This is called transfer learning. Instead of learning from scratch, the model already understands basic features like edges, texture, shapes. Now it just needs to adapt to road defects. This dramatically improves training speed and accuracy. Optimizer equals to SGD. We use the SGD instead of AtomW. Why? Because SGD is lighter on CPU, uses less memory, and is more stable for small datasets. AtomW is powerful but heavier computationally. Verbose equals to true. This prints detailed training logs like loss values, MAP scores, precision recall, very useful for monitoring training progress. So, in simple terms, if we say what this does is that it first loads the lightweight YOLO model, forces training on CPU, uses transfer learning, keeps the batch size small to avoid crashes, and trains for 100 epos safely. Perfect setup for training on custom road defect dataset model on a normal laptop.